Hey yo, back for section 6, last section in chapter 6. We're dealing with complex numbers here. I'm going to split it. I don't know where yet. We'll do an introduction and then probably do addition, subtraction, multiplication, division all together, or I might split those separate. So complex numbers, this is where we start talking about something a little confusing compared to what we've been taught up to this point. There is a number that exists called I that represents the square root of -1, which means I squared is -1. When we get down to it, the goal for this section is thinking if A is positive, then we can have a square root of a negative number. But what we have to do is draw that negative out as I. So we can write this as I times the square root of A. Square root of -A, pull that negative out, make it an I, and then we have the square root of A, so we can solve for that. A little later we're going to get to this idea, I'm just going to put it here now, of I, it's obviously just itself, but when we square it, it's equal to -1. I squared is -1. That's a value, that's a key value that we have to keep in mind through this whole section, and then the goal once we go beyond I squared is just asking how many I squareds can we get. I squared is -1, so any I squared I can pull out is a -1. So when we have an I cubed, I can pull out one I squared, and I multiply it by the I that's left over. I squared times I to the first, 2 plus 1 is 3. So when we have anything bigger than squared, the whole goal is how many squareds can I get out. Every I squared I pulled out is a negative. So when we have an odd exponent, we are pulling out some amount of squareds, -1s, and then an I. There's always going to be an I left. However, when we have an even number, then we are always pulling, an even exponent, we are always pulling out an even amount of -1s, which means we always have -1 times -1 is 1. So when we, beyond squared, when we have an even exponent, we're going to end up with -1. Okay, so a couple simple examples they start us with just to get the idea. Examples 1 through 4, they say now we can have square root of -25 because that negative, I'm going to circle it, this negative becomes I. And so what we actually have is I times, that might be too small, I times the square root of 25, which is 5i, because the square root of 25 is 5i. Whenever you see a negative inside the radical symbol, pull it out. So then they give us -49. There's the, I'm going to do it again, I'll do my little arrow. The negative becomes an I, we're left with square root of 49. The square root of 49 is 7, so we pull it out. 7 times I is 7i. Then they go to one that's not a perfect square, -12. Well, first off, pull out an I. So we have I times square root of 12, and square root of 12 is 3 times 4. I can pull the square root of 4 out. I pull it out, it's a 2. Square root of 4 is 2. 2 times I. I'm left with square root of 3 inside. And then square root of, that's it. Those are the ones to really look at. If it's a prime, we can just pull out a negative. If we see a negative, we pull it out. So the whole idea here, if we see a negative, pull it out, make it an I, and then focus on the positive numbers left over. I would just pull it out right at the beginning to avoid any confusion. Okay, so let me go ahead and erase this. I'll leave that piece because that'll come into play a little bit later. Oh, actually right now. Imagine that. Crazy times, crazy times. So example 5. We have I to the 30. They're trying to get us to understand this rationale of, ooh, I to the 30, that's a big one. What can we do with it? Well, what we want to do is say, I squared. I know I have some in there. How many can I get out of there? In this case, we have an even number, so I can pull an even amount of them out. Well, not an even amount, but I can pull I squareds out and not have a remainder. I know I'm not going to have a single I left. If that was 31, I'd have a single I left. But what I can do is say I squared to the 15th, because when I raise an exponent to an exponent, I multiply. 2 times 15 is 30. So how many I squareds can I get out? Well, I can get 15 of them out of there. I can get 15 I squareds out. What that means, I squared is -1. So I have -1 to the 15th. If it was 5, I'd just write them all out. To the 15th. That means an odd amount. So think of it in threes. If I had an even amount, 14, I'd end up with two with pairs, I should say. I'd end up with pairs, and the negative times the negative would go away, make it a positive. I have an odd number. So whenever I have an odd exponent, then I'm going to have a -1 when I'm dealing with I squareds, and I pull them out of there. Example 6 gives us I to the 11th. So I say, well, how many I squareds can I get? I know that I can get 5 out of there. 5 times 2 is 10. It would leave me with an I left over. 5 times 2 is 10, times I individually gives me my 11th. So 5 times 2 is 10, I to the first, 10 plus 1 is 11. Now, I have I squared to the 5th. Remember, I'll rewrite it. Remember, I squared is -1. So I have -1 to the 5th times I. It's an odd number, odd exponent. I know I have a negative. I know I have -1 because it's odd, and I have an I. So a -I. And then they give us I to the 40th, right? I to the 40th. So here, I squared. How many can I get? I can get 20. Now they gave me an even amount. So with an even amount, I know I squared is -1. I'm going to have pairs. I'm going to have 10 pairs of them. I times I, or -1 times -1 is positive. So I am going to end up with a +1. There's a few different scenarios they gave us to think about. Odd exponents, then I have a -1. And then it depends on how many I have left over. Odd exponents, -1. In this case, I had an I left over, so -I. Even exponent, you're always going to have a positive. So an even exponent, I have -1 times -1 is 1. Okay? Now, they move to our next idea, where they give us a complex number, how they can write it out with A and B involved, some variables involved. And they say the complex number is A plus BI, where A is the real part, and B is the imaginary part. A plus BI. This chunk is imaginary. A is real. A is something, some value. So, I said, remember, two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. It doesn't matter if two are going to be equal if the left equals the right. That doesn't change. So example 8, this is a little different thinking here. Example 8 says find x and y. Find x and y if 3x plus 4i equals 12 minus 8yi. And I mentioned use the rule up above to try and solve this. Well, the rule up apart that I didn't write, the rule up above that I mentioned that I didn't write in this case because of my small whiteboard, is knowing that the real part has to equal the imaginary part. My real part, remember this, that's real. That's a real value. I don't have I. That's a real value. So the real part means 3x equal 12. Remember this, the real has to equal the imaginary. Here's my real on the left. I could even say the real on the left, the real on the left is 3x. The real on the right is 12. When I solve that, x equals 4. I'm done. I solved x. That's how I did it. I ignored the rest of it. My imaginary part is what's left. 4i, that's my imaginary piece on the left, minus 8yi is my imaginary part over on the right. So that has to equal that. Well, I have a negative 8yi. Whoops. I'm going to divide by a negative 8i. And my y, if I look at this, if I'm thinking this route with an I, you're going to see the way the book does it. But I'm thinking, well, i's, I got to get everything over together. I need my y to go away. We can think about this as the imaginary part. I think that's how the book handles it. Let me double check. Yeah, the way the book handles it, they make it go away right from the get-go, I believe. No, they leave it in there for a minute. When we're dealing with this, we mean the imaginary part. Because it's the imaginary part, we can think of it as 4 equals negative 8y. We don't have to worry about the I, because I know we've got our I rules, but in this case, the I tells us that is the imaginary part. 4 imaginary, negative 8y imaginary. So we write it all out to think, how do we get y? We get everything over here. But then we're just kind of ignoring the I. You can leave it in and just know y equals negative 1/2, and you can take it out at the end, or you can take it out right away when you're solving the two pieces. Know that y is with the imaginary, x is with the real. My kids are getting a little riled up out there, so we're going to do one more and we'll probably cut off after that. Example 9. Find x and y if 4x minus 3 plus 7i equals 5 plus 2y minus 1i. Okay, so we're going to distribute this. I'm going to write this as 4x minus 3 plus 7i equals 5. You don't really need the parentheses. It's just saying the only piece that's imaginary is the piece with an I. Equals 5, and then I've got to distribute. Plus 2yi minus I. Now I can kind of think of this and combine everything. So, my real part, I have 4x minus 3 on the left, and I have 5. So I'm going to go this way to solve. So I have a 4x, and I just add 3 equals 8. X equals 2. There's my 2. Now my imaginary part, now I'm going to write it without the i's. My imaginary part is, basically think of it, I guess I didn't have to distribute, I think the book did though. Think of it as 2y minus 1 and 7y, or 7i. I have 7i. That's my imaginary part. My imaginary part over here is 2y minus 1. Now when I add my 1, I end up with 8 equals 2y. Y equals 4. I think that's all I wanted to do on this one. Yeah, that's all I wanted to do on this one. I believe the book distributed that, but you don't need to. It's easier to think of it as that chunk as I. So this is thinking imaginary numbers. This is the introduction of how we deal with them. When we move to addition and subtraction, we're at 15 minutes. I'll do addition and subtraction. Well, no, I'm going to do it right now. You know what? It's simple. This is more difficult than addition and subtraction. You got to put them all together and think of them as real and imaginary. Well, when we start adding and subtracting, you're just adding real parts and imaginary parts, x's, y's. You're still thinking similar terms. So add and subtract. We'll jump to example 10 real quick. Example 10 gives us 3 plus 4i plus 7 minus 6i. Literally, look for like terms. In this case, I is our like term. 3 and 7 are whole numbers. I can add 3 and 7, they're numbers. That's easy, 3 and 7. And I can take my 4i minus 6i and combine those. So I'm thinking of these two different pieces. I shouldn't have written it that way. That looks like multiplication. I'll say plus 4i minus 6i. So I have 10 and I have 10 i's. 10 minus 10i. I don't know if the book factors out a 10. They might. Whoops. All of that, and then I made a mistake. Darn it. The kids were banging at the door and I screwed up. So what I have is minus 2i. 10 minus 2i. Now I can factor a 2 out, but I don't think the book does. The book just leaves it as 10 minus 2i. So we'll just leave it as 10 minus 2i. To say there's my number, there's my imaginary. Now I'll try to end strong after that mistake. Example 11, we have a 7 plus 3i minus 5 plus 6i. Okay, there's advantages to working from home and disadvantages to working from home. My disadvantage is having 3 kids running around banging at the door. So I might as well distribute first. I don't need these in parentheses because this quantity doesn't matter. I'm concerned with my numbers, my variables, my imaginaries. I just want sames, anything that's the same. I'm going to distribute my negative. So minus 5 minus 6i. I have 7 minus 5 equals 2. I have 3i minus 6i equals a negative 3i. So my answer is 2 minus 3i. Addition and subtraction, simple. Addition and subtraction is easier than that initial part of solving for variables. So I'll come back at you with part 2 where I'll do multiplication and division all together in the next video. We'll see you then.